So here we are, we're making some models now, some physical models rather than mathematical models, although we are actually making a mathematical model as well. Let's see if we can help Rob to analyze the scale and the time taken. So the question, without any explanation to start with, asks us to calculate the product moment correlation coefficient between log t and log s. So we better start calculating the values of log t and log s. So here's the table which has got all blanks in it, and when we take the log of 2.1 we get a value, the log of 7.1 we get a value, etc, etc, and when we pop those into this table, these are the values we get. Now when we pop those values into the statistics module in the calculator, I'm sure there's one whether you're using a graphical calculator or a standard non-graphical calculator, you can pop those data in to your calculator and get the figure for R, which is very, very close to 1, remarkably close. Well, how does that then confirm Rob's belief? Well, let's have a look at this. We know that the relationship is of the form t equals k times s to the n, and when we take logs of both sides, we get log t equals log of k s to the n. So log t equals log k plus n times log s. Now the two variables in this equation are s and t, or if you like, log s and log t. So this looks like y equals mx plus c, and so with the this is the m, that's the x, that's the c, and that's the y. So if when we take logs of both sides we get a product moment correlation coefficient which is equal to 1 or very close to 1, then that confirms that the original model t equals k s to the n is a valid model to look at. So if t equals k times s to the n, as I said, log t equals log k plus n log s, which would be linear. And because we're getting a product moment correlation coefficient very close to 1, that shows that all of these points are very, very close to a straight line. And so that confirms the linearity of this this model here. So now we've got to find the equation of the regression line of log t on log s. Well, if you put all of this data into your calculator to find the product moment correlation coefficient, then the chances are that it will give you the values of a and b. This is a and b, which are in the equation y equals a plus b times x. So my calculator gave me that value for a and that value for b. So the equation of the regression line is this, a plus bx, or log s in this case, because we didn't use x, we used the values of logs, the logs of the s values. I hope you're following that. Okay, so that's the equation of the regression line of log t on log s. Now when we compare that with the equation t equals ks to the n, this one here, and we take the logs of that again. We'd say log t equals log k plus n log s. We can see that 0.4310 is log k. So that's what I've written down there. And in a moment, we'll also find that n is equal to 1.3044. But for a moment, if log k is 0.4310, then 10 to the power of that, the k is 2.70 to 3 significant figures. And as I said a moment ago, n is 1.3044 or 1.30 to 3 significant figures. So there we are. That's the values of k and n. So we could actually write the model out now, couldn't we? We could say t equals 2.70 times s to the power 1.30. So that's the model. If the question asked us to write down the actual model, then we could do that. But it didn't ask us to do that. It just asked us to find the values of k and n, which we did there. So there we are.